to graphene, which is only one atom thick, here you have one layer that is composed of three atoms. So depending on how you stack the three layers of atoms, you will have very different crystal structure. And so if we look at this cross-section view from this single layer of TMDs, for example, this is typically MOS2, you will have a stacking order of ABA stacking. Okay, so the two sulfur here in yellow, or the two chalcogen are on top of each other. So this creates this hexagonal symmetry that is known as 1H if it's single layer, or 2H phase. But you can also have a stacking where the stacking sequence is ABC, so that the two chalcogen are rotated by 60 degrees. And this will give you this 1T phase that you see here. For the typical example is TiS2. You can also have TMDs, for example, rhenium sulfide or tungsten like telluride, that will have this distorted 1T prime phase. So it could be either like a diamond cluster, so you will have a cluster of these transition metals in the form of a diamond, or you can also have this zigzag chain that you have typically with this tungsten ditelluride. So this works for single layer, but if you stack, then you can also stack similar to graphene. You can have ABA stacking. So here, now I'm talking of the stacking of the different nanosheets. So ABA stacking, this is known as the 2H phase, or you can have this ABC stacking, the 3R phase. So this is very, same as graphite. So, if we go back to the periodic table, here now I colored the periodic table with the different types of structures. So we know that this group 4, 9, and 10 will typically give you this 1T phase. So 1T phase is here. So the best example is TiS2, as I mentioned before. So this is a single layer that is observed by scanning transmission electron microscope, okay? STEM. The group 5 and 6 could be either 2H or 1T, or 1T prime, for example, for the tungsten or the molybdenum ditelluride. So this hexagonal pattern is here. The quality of the STM image is not so clear, but you can see some contrast here. I will show you better on the next slide, but you can see some contrast here that is coming from the sulfur, because now you have two sulfur on top of each other. So the contrast is twice larger compared to the 1T phase, where you have only one sulfur at each position. And you have this current 7 that is typically correspond to this distorted structure. So the best example is this rhenium sulfide. So you can see here the diamond cluster of the rhenium atoms, or you can have this zigzag chain here from this tungsten ditelluride. Okay. Now, what we have learned with having like 15 years experience with 2D materials is that these materials are very easy to engineer. We can tune the properties of this material by functionalizing the material with covalently grafting some molecules on the nanosheets. You can also engineer with phases, so you can control the structure of this 2D material, so especially it has been developed for this 2D TMDs. You can apply some strain, so you can compress or have a tensile strain applied on the nanosheets. And you can also dope, so you can substitute some atoms, some chalcogen or some metals, and tune the properties of this material. Or you can create some defects. Either you want to control the density of defects, or even the position or the nature of the defects, in order to tune the properties. So here I summarize on these slides the different strategies that are currently being pursued, being investigated by the community. And today I will show you 3 examples that we are currently pursuing in my group about phase engineering, about functionalization engineering, about defects engineering. And I will show you how we can do the methods that we propose, and what can we do with this engineered material. So I will first start with phase engineering, because this is what historically I have started with. And as I've mentioned before, TMDs can exist with different types of phases. Okay? This group 6 is particularly interested because it can exist with either the 1H phase or the 1T phase. Okay? So two different symmetry, hexagonal or trigonal symmetry. And this can be controlled by charging the nanosheets. So this is not new. Actually, if you see here, this has been shown in 1986, okay, by a group in Canada from Johnson and et al., where they initially investigated this bulk MOS2 as a cathode for lithium-ion battery. And what they did is they discharged the material, they discharged the battery, so they intercalate lithium in between the sheets of MOS2. And what they realized is they observed different phases, different crystal structure, and second, they observed that they can exfoliate material. So if you look at the papers from this group, they have one paper, I think in the 80s, where the title is single layer MOS2. Okay, much earlier than the first paper on graphene. So we used these methods. Again, we didn't do anything new here, but we followed the approach where we typically buy this 2H MX2. So here, typically this works for this group 6 TMDs. So it works for molysulfide, molydiselenide, tungsten diselenide, tungsten disulfide. Okay. What we do, we mix this bulk powder of 2H phase. This is the thermodynamically stable phase for this material. And then we mix with reducing agent such as butyl lithium. And this reducing agent will, there will be electrochemical reactions. And the lithium, the butyl will will give one electron to the MOS2. And so you have to compensate the charge, so the lithium will intercalate at the same time. So you charge it negatively in nanosheets, and you intercalate in the lithium cation. So this is how it works, as a bulk reactions. And at the end, you have intercalated this bulk powder. You can exfoliate in water, do some centrifugation steps. You can purify the non-exfoliated material, and at the end, you will have a solution of 100% single, or close to 100% single layer nanosheets in solution. Doesn't mean that the reaction is 100% efficient, but it's very easy to separate, bilayer, trilayer, and bulk or aggregates from the single layer. So at the end, you have a solution in water, which is also quite, easy to work with, of single layer nanosheets with this 1T phase. So the typical image of these nanosheets are shown here. This is an AFM, atomic force microscopy image of a deposit of MOS2 nanosheets on silicon dioxide wafer. And so in yellow, you have this these nanosheets. The color contrast is coming from the height of the sample of the nanosheets. So the brown region is just the substrate. The yellowish is the nanosheets. So you see, it's roughly the same contrast, which tells you this is the same thickness. So the thickness here is about 1 to 1.2 nanometer, which is coherent. This is coherent with the single layer of the nanosheets, because this is chemically exfoliated, so we still have some water traps between the nanosheets and the substrate. If you look at the size dispersion, so we have the nanosheets in length are around 200 nanometer. This is the length. This is the width of the nanosheets. So you see, we have a kind of Gaussian distribution of the length size of the nanosheets. So this process has been later revisited by theory people, and this figure has been taken from this paper from Canet all published in GPhys MC in 2014, where they actually predicted the phase transition upon charging and discharging the MOS2 nanosheets. So you start with this MOS2, so again, this is 2H, this is thermodynamically stable. What they predicted is up to 20%, higher than 20% intercalation. So if you have 20% excess of electrons in your nanosheets, you will induce a phase transition, and you will create this, ideally distorted 1T phase. And then, if you further intercalate up to 100%, then you will have a stoichiometry of Li1 MOS2. And you will, since you have a large excess of electrons, the nanosheets will have to adjust, and the most stable structure to adjust this large excess of charge is this diamond shape that we have seen for RES2 on my previous slide. And this material, so this distorted 1T phase with diamond clustering of the molybdenum atoms, can later relax into zigzag chain when you de-intercalate. So typically this is what happens when you mix your intercalate MOS2 powder with water. Some of the charges will react with water. It's going to give you some hydrogen bubbles you will see in the solution. And this, so as a consequence, some of the charge are being removed from the nanosheets, and the material will adopt this zigzag chain. So here they call it ZT. So it's still 1T, distorted 1T phase. And finally, if you anneal the material, so experimentally we found at 300 for like half an hour on the near atmosphere is enough to quench this distorted 1T phase, and you restore almost completely this hexagonal 2H phase. Okay, so you can kind of have a circle of phase transition. So this is some STEM images of single layer of MOS2 that has been chemically exfoliated, just to show you the different phases that we have. So this is a single layer again. This is the same nanosheet, so we have in plane heterostructure with different types of phases. So the 2H phase is shown here in red. This red region is magnified here. So you can see you have some white contrast here. The strong contrast is coming from the molybdenum atoms, because the contrast in STM comes from the Z number. So the molybdenum has a higher Z, so higher contrast. And then here you have the contrast from the sulfur. So you can recognize this hexagonal symmetry that we expect from the 2H phase. In yellow, you have this ideal 1T phase, so not distorted 1T phase. And it's a bit difficult to see, but you see we lose some of the contrast here from the molybdenum. And this, we can just recognize this triangle here from the molybdenum atoms. And the sulfur here, the contrast is gone because we have only one sulfur, as I mentioned before. So we have only one sulfur at each position. So the contrast here is 2 times lower than here, where we have the 2 sulfur on top of each other. So this is why we don't see the sulfur, and we can use this to recognize and identify this ideal 1T phase. And then the last region that we have on our single layer of MOS2 is this region here in blue, where you can see some patterns here. That is this zigzag chain that was expected from the theoreticians, and this is what also we observe experimentally. And you have this zigzag clustering, this zigzag chain from the clusters of molybdenum atoms. Okay, this is for MOS2, but we also have the same for tungsten disulfide. In the case of tungsten disulfide, we found we have higher amount of pattern of zigzag chains, sorry. And very interestingly is if you compare this the lattice parameter of 1T phase compared to the 2H phase, we have some strain that is also built up during this intercalation reaction. And here I've shown you we were able to analyze the strain in the single layer of chemically exfoliated 1T phase or 1T prime phase of tungsten disulfide. And we have some regions under tensile strain and some region here in black under compression. So we have a highly strained material. This is the as exfoliated material, so after the lithium intercalation. Once we remove the strain by annealing, so again 300 degrees on the inert atmosphere, then we recover this 2H phase, and then when you compute this strain tensor map, we have pretty flat image, showing that we have no strain that is present after this annealing. In the case of tungsten disulfide, we cannot recover 100% of the 2H phase, but we found it's about 80%. Because the 1T phase of tungsten disulfide is actually much more stable than the 1T phase of MOS2. And this has also been shown previously in the literature.
And what temperature you will do?
300. So the question we ask ourselves is, okay, we know from the TEM we can identify 1T phase, 1T prime phase. But can we, TEM is very time consuming, so can we quantify easily the amount of 1T phase or amount of 1T prime phase? And we did XPS, and what we observe is, if you look at this as deposited material, actually the signals, this is from the molybdenum 3D, and this spectra here are from the molybdenum S2P, the sulfur S2P. What we see is the signals are actually split into two signals that we attributed to the signal from the 1T phase, or 1T or 1T prime, we actually cannot say, and the signal from the 2H phase. So here in the green, you have the signals from the 1T phase, and in the doublets from the 1T phase, and then in red, you have the doublets from the 2H phase. So you have the same split in both molybdenum 3D and sulfur 2P spectrum. As we increase the temperature, we know from the TEM and also the Raman spectroscopy that the 1T phase is getting quenched. And this is also what we see here in XPS. And you see after, around maybe 150 or between 150 and 200, it's progressively decreasing. So the nice thing with XPS is you can integrate the peaks and you can quantify the amount of the different signals. So we can quantify the amount of 1T phase and 2H phase. And this is what you see here. So in the beginning we have about 50% 2H, 50% 1T phase. As you increase the temperature, you see the signals from the 1T phase decreases close to 0%, and at the same time you have 100% 2H phase. So XPS is actually a very powerful technique, relatively easy to perform, and we can probe large region of the sample. So we have very good numbers, very good statistics. So we're confident about the amount of the different phases. And this works for all the different TMDs. So you see this is for molysulfide, tungsten sulfide, and molybdenum selenide. So this is the amount of 1T phase as function of temperature. If you take the derivative of this, then you can estimate the phase transition temperature, and we found it's about 100 degrees for molysulfide, I think around 160 for molybdenum diselenide, and about 200 for tungsten disulfide. And actually this agrees with previous measurements that have been obtained from differential calorimetry measurements. Most importantly, we can exfoliate this material using these methods and have single layer in solution. We can make films, we can make single layer films of this MOS2, WS2, MOSC2. And if we restore the 2H phase, then we can have material that are semiconducting. And what we know is when these TMDs are single layer and semiconducting, they are direct bandgap semiconductors, and they're supposed to emit some photoluminescence. And this is what we measure experimentally. So this is just for MOS2 as function of the temperature. So you see in the beginning the same film is not showing any PL. As you increase the temperature, and especially after 300 degrees, then the PL is fully restored, because we go from metallic to semiconducting material. And for the different types of TMDs, we have PL that is consistent with mechanically exfoliated or civilly grown TMDs. So at that time, it was the first methods to prepare chemically exfoliated nanosheets of TMDs that are truly single layer and that shows some PL signals. Of course, the signal is not as strong as what you would have from mechanically exfoliated or civilly grown TMDs, but I would say it's rather good for chemically exfoliated materials. Okay, and then So we understand, how we can tune the phase, how we can control the phase. So the question that we had was, okay, how can we use this phase engineering? And one of the idea that we had was to use phase engineering for electronics. Because when you use 2D material, semiconducting 2D materials such as this group 6 TMDs, usually the Schottky barrier increases dramatically and you decrease the thickness of the material. So single layer transistor made of MOS2, for example, or tungsten sulfide, have a high Schottky barrier, and that kills the FET performance of the material. So the idea that we had was, can we engineer the structure of this material so that we can pattern a single layer of TMDs with metallic regions by applying these reducing methods, while keeping some region with the semiconducting phase. So we have an in-plane heterostructure with a metallic 1T phase and 2H semiconducting material. So what we did is quite simple. We just pattern the substrate, we pattern the MOS2 so that we can expose some part of the sample to the butyl lithium, the reducing agent, and some are capped with PMMA, so they cannot react. And so this is very relatively simple methods of patterning using PMMA. And this is a proof of concept here where we just pattern everything, we cover everything with PMMA, and then we pattern this region of the single layer MOS2 so that this is open, and this was left open to react with butyl lithium and converting to this 1T phase, and then we perform conducting AFM, and the darker regions here are showing that they are conducting, okay? Because we locally change the structure of the material, and we create this 1T phase. You see that the reaction is not 100% efficient. We still have some regions that are not fully converted, but we have enough regions that are conducting so that we can inject electrons efficiently into the semiconducting part of the sample. So once you have this, you just deposit gold contact on this 1T phase, so we can have here the interface between metallic gold and metallic MOS2. So we have much reduced Schottky barrier, and then we have a homojunction here between this MOS2 1T phase and 2H phase. So again the Schottky barrier is much less compared to gold 2H MOS2. So we did actually, this is from the PhD student at that time, Rajesh Kapura. He did this, and then we made this TLC method, so we can measure at increasing channel lengths, and then we measure just the resistance, and this is the resistance of the devices for increasing channel lengths. So you can have a slope. Here you can get you can extrapolate the resistance with 0 channel, which gives you twice the contact resistance. So we found that using this method with 1T phase as a contact, we can reduce significantly the contact resistance compared to 2H contacts. And when you make devices in red, you have this fully converted, so both the contacts and the channel is converted, so there is no effect of the gate. This is expected because now you have a conducting MOS2, so there's no effect of the gate. This makes sense. And in black, you have 2H contact, and then here you have 1T phase contact. So we have improved mobility, improved on current, improved threshold voltage. So this shows that this phase engineering could be used to decrease the contact resistance and improving the FET performance. So following this idea, we say, okay, we know that MOS2 and 1T phase of MOS2 was very active for hydrogen evolution reactions. But one thing is, when you do electrocatalysis, that is often overlooked is the influence of contact resistance. So the influence of the resistance to transfer electrons. Because when you do electrocatalysis, for example, if you do hydrogen, so if you work in acidic conditions, you have the reaction 2H plus 2 electrons gives H2. So you need to convert, you need to inject electrons to the active sites of the MOS2 to react. So the contact resistance, similar to FETs, should be very important. And in the literature, it's very difficult to get access to this. And actually, I think this is one of the first report where we gave some values, or at least we showed the influence of the contact resistance. So if we had the same strategy as before, we were able to transfer a single layer of MOS2 that it was CVD grown, so the contrast is not so good, but you can barely see some MOS2 here on the silicon dioxide wafer. And then we converted locally the contacts, then we put the gold contact. We cover everything else with PMMA, so only one flake is exposed, and we contact it with 2 electrodes so that we can sweep the device. And with knowing the resistivity of MOS2, we can estimate. So this is very rough estimation because this is not ideal configuration for the electrodes, but we can roughly estimate the contact resistance. And we can do this, we can also pattern the substrate so we can expose only the surface of the nanosheets or only the edges. So here everything is covered with PMMA, this region is open, and the flake is like this. So we can contact here with either 2H contact or 1T contact. And we expose mostly only the edges, and a little bit, of course, of the surface. So the surface, the device looks like this. So we have gold electrodes that are converging in the center of the chip. And then here we deposit the MOS2 nanosheets, and then we using microfabrication techniques, we can contact individually the single flake. I'm not sure if you are familiar with electrocatalysis, but when you do electrocatalysis, typically you use 3 electrodes. One is the working electrode. This is basically to probe your sample. The counter electrode is to detect is to have a flow of electrons between your working electrode and your catalyst and the counter electrode. And the reference is to control perfectly the potential of this working electrode. So basically what we do now is we're going to sweep the potential between the reference electrode and the working electrode, and we will measure the current. And this is what you see here. So in the beginning, at low potential, there's not enough, let's say, energy to activate the reactions, and the current is 0 because there's no reactions. Once there is reactions, since it involves electrons, it will create some current. Okay? This is what you see here, around 250 millivolts. This is the same type of MOS2. The only difference is the contact resistance. So we fabricated like 20 or 30 devices, and we were able to get some devices with better contact resistance, so lower contact resistance, some with higher. And then we measure systematically the devices. And you see that for the same material, again, MOS2 is the same batch, CVD grown. With high contact resistance, there is no current. And as you decrease the contact resistance, then you start to see a strong improvement of the electrocatalytic activity. So this is kind of obvious. If you have a high contact resistance, you cannot inject electrons, so there's no reaction. If you have a very low contact resistance, then it's very easy to contact the material, and then you will be able to activate your electrocatalytic material. The other way to look at these results is to plot the turnover frequency. So the turnover frequency corresponds to the numbers of hydrogen being evolved per active site per second. So a turnover frequency of 100, for example, means that you have 100 molecules per active site that are evolved per second. So this is the same data. Actually, it's just some analysis. And the same trend, I think it's easier to see here. When you have a high contact resistance, there's very, very low turnover frequency. As you increase, then you see that you have a strong improvement of the contact resistance.
This is direct contact 2H MOS2, right? Or do you have 1T?
So the highest contact resistance is with 2H, and then the lowest is with 1T. And then some contact resistance with 2H were better than the others, so we were able to have some variation in the contact resistance. But the contact resistance, the best one is always with 1T phase. And okay, so I didn't. So I have another slide on this. But basically, what we see here is if you have the same electrocatalytic material, no matter if it's good or bad, I mean, it has to be good, of course, but if it's good, meaning thermodynamically active, but you have a high contact resistance, you will not get any activity. So in this paper, we actually show that contact resistance is very important. And if you have very high contact resistance, you will not be able to evaluate the true activity of your material. And more recently, I think this is just put one slide on this, because this is new project in my group. We were trying to explore novel application of this phase for electrocatalysis. And one of the projects that we have is to do this electrochemical reduction on organic molecule. And the idea is to actually the original idea is to neutralize some nasty chemicals. So, for example, the DMS, it's a simulant for mustard gas, which is a chemical weapon. And we wanted to use this and show that we can convert this into a safer molecule instead of just burning it or just burning typically. We can use electrochemistry to convert it to maybe something useful. And here, as an example, since we cannot work with dangerous chemicals in the lab, we use this DMS. The idea was, okay, do we have is there any way to convert this sulfur and maybe oxidize it? And then here I'm showing you just some preliminary results. This is the results from 1T phase, 2H phase, and platinum nanoparticles supported on porous carbon. So here we have chemically exfoliated. So this is not one single flake. This is like a bunch of flakes that are being drop casted on an electrode. And then we just test it, and then what we observe is we also observe an improvement when using this metallic 1T phase, and we have activity that is very similar to platinum if you look at the turnover frequency. So again, the numbers of reactions per active site per seconds. We see that platinum is still a bit better, but we have a very clear improvement when using this metallic 1T phase. We believe it's the metallic nature is improving the electrocatalytic behavior for this particular reaction as well. So, maybe if I come in future, I will have some more results on this. But this shows you that there may be some other application for this 1T phase in electrocatalysis. Okay, so now I will show you a different way to engineer two-dimensional material using functionalization. This is something I have started since I have my position in Montpellier, and the idea is to modify these TMDs with covalent functionalization. So on this slide, I've shown you two examples of functionalization that have been reported in the literature. One is based on thiol, treating these TMDs with thiol. So thiol it has these SH groups that is supposed to react at the defect site. So when you have a sulfur vacancies, people have predicted that this thiol can react and then can coordinate at the vacancy site, and it could be a way to actually heal the nanosheets. So after you have this functionalized TMDs where this thiol is coordinated at the defects, you do a mild treatment, a thermal treatment, and this group leaves, and then you have healed the sample. This actually has been recently revisited in this paper. If you want to know more about this, where the claim is maybe not as simple as it is, maybe it's just dimerization of the reactants on the surface. So the other approach that has been reported, this is from Ali Javik's group at Berkeley, where they functionalize with NO2, and the same thing. The mechanism is based on coordinating this NO2 at the vacancy site of this tungsten diselenide. And they were able to demonstrate that after functionalization, actually the behavior is very different. You have a material that is more conducting and behaves as a metal with no effect of the gate. Okay. So these two approaches are actually defect mediated strategy. The idea that we had was to use again this 1T phase. In particular, not the 1T phase, but this excess of electrons. Because this excess of electrons can, trigger chemical reactions. And from my undergrad courses, I know that this looks like this could be like used in the substitution reactions. So what we did is we treated this negatively charged, so with excess of electrons, TMD nanosheets, and we treated it with organohalide molecule. Like typically, we used iodine as a leading group, and the way I understand it is more like a substitution reaction. So the excess of electrons will react this positively charged carbon bonded to the iodine, and then it will create a covalent functionalization and leaving the iodine as a leading group. And as a blank reaction, we also treat it with iodine just to make sure that we don't create a reaction just because of the iodine itself. I will go just briefly on this. This is just to confirm that we have covalent functionalization. This is the FTIR spectra. So this is the molecule. So here we functionalize with iodomethane. This is actually this dimethyl sulfide, where you have the methyl bonded to the sulfur, just to see that we have similar signals. And this is the functionalized TMDs, so molybdenum sulfide, tungsten sulfide, molybdenum diselenide, that has been functionalized with methyl groups. So what is good is we see the methyl groups. Okay, this is expected, but more importantly, we see this SC vibration, which shows that it is covalent. What is more interesting is if we look at molybdenum sulfide and tungsten disulfide. So here we keep the same chalcogen, so it's sulfur, but we change the metals. There's no peak shift. When we keep the same metal but change the chalcogen from sulfur to selenium, then you see the peak is clearly shifted. So this suggested that the covalent attachment is on the sulfur, on the chalcogen atoms. We also got some confirmation here on the XPS result. So here we functionalize with iodoacetamide. So acetamide contains these NH groups, so we can detect the nitrogen. This is what you see here from the functionalization. So then we can use this to estimate the extent of functionalization on the nanosheets. This is the S2P regions, and you see this is before and after functionalization. So you see we got some additional signals here. The peaks are clearly sharper because we have these signals now from these SC bonds. Okay, so this is an indirect way to confirm it's covalently functionalized. The interesting result is we apply this strategy on CVD grown sample. Again, this is the same types of reaction. We just use high quality CVD grown sample. This is the flake that we use here, for example. We contacted it with gold pad. This is just to stick the sample on the substrate so that it doesn't get washed away during the chemical reactions. This is the pristine PL here from the 2H phase around 1.8 eV. This is 1T phase, so after this treatment with beta lithium, so it's converting to metallic 1T phase, and this metallic region quench the PL. And then after functionalization, we restore, very surprisingly, we restore the PL. The PL is slightly shifted at 1.9 eV, but very interestingly, we have this new signal here at around 1.6 eV. And we can modulate these signals, and we believe this because of the extent of functionalization. Unfortunately, this is not a new peak of absorption. This is more related to defects. So we did some absorption measurements, and there's no absorption peak at 1.6 eV. So we believe this is more like defects bonded excitons.
Is there any way of pushing this shifted peak to more into the near infrared region? Using, for example, different functioning groups?
We didn't investigate this. I believe this is really related to defects. I'm not sure the nature of the functionalization is important, but we didn't investigate.
I think it's making modification in the band gap.
Yeah, but
okay, we can. The second question related to this question. You showed from 2H phase to 1T phase we need to convert.
Yeah.
But this is mostly sulfur-based materials.
Mm-hmm.
I am wondering the WSE2, the most common material research community is using. For this material, do you have?
So that's actually a good question. I didn't mention because from my experience, it's very easy to oxidize. So we tried. I tried a couple of times. Just chemical exfoliation. I didn't try to convert to do any reaction with CVD chrome. But on chemically exfoliated materials, I have like 50% tungsten oxide after the reactions. So it was too oxidized to work with. So the results I'm showing today, there's no, or we cannot detect any oxides. But tungsten diselenide, for some reason, is very sensitive toward oxidation.
Yeah, because it would be great because its emission already near
yeah, it would be.
This kind of functionalization probably it would be more inventive.
So we haven't tried much on this. We tried in water, which is of course not the best solvent to prevent oxidation. So there might be some ways to do this reaction in our organic solvent, high nitrous, but we didn't do it. So I think it could be interesting. The quality of the flakes, by the way, is very important for the functionalization. We tried with a lot of different flakes, CVD grown. Very few are surviving the treatment. So we have this, batch from a Giants group at that time, and for some reason their sample worked very well, better than ours.
Sorry, you said after the functionalize the 1T ammonium disulfide, the PL peak has been restored, right?
Yeah.
So what's the reason behind this extreme?
Actually, we don't know why. We believe it's still 1T phase because we detect the Raman signal from this restored 1T phase. But yeah, more like chemist, so this will, I think, require more, maybe help from the theoreticians to understand. I've discussed with some people. They say it maybe because since it's at some on the surface, we can create some asymmetry. We can functionalize only the surface, so this could create some change in the material. But, I cannot answer more. Okay. So since I moved to this membrane institute, one of the thing I wrote on my application was to use these TMDs or use these 2D materials to make membranes. And one way to use one way to use two-dimensional materials is actually to restack them to make these nano capillaries, where you can control the size, in principle control the size, the space between the nanosheets, and this interior spacing can seal efficiently molecules depending on the size. And the idea that we had was, okay, we can functionalize, so why not trying to functionalize these TMDs, stack them, and have like nano capillaries with different surface chemistry. So we can functionalize with methyl, that is hydrophobic. We can functionalize with acetamide or ethanol functions that are more hydrophilic, and that maybe influences the sieving performance of the membrane. So this is some example from the literature. This field has been, proposed by the Manchester group, Raoul Nair. They mostly work on graphene oxide films, so they exfoliate and they filter graphene oxide by vacuum filtration. So very easy to make. You can make freestanding membranes, and when you look at the cross section, you have these very highly aligned nanosheets where you have these nanocapillaries, 2D capillaries. This is, for example, the cross section here. And in the first paper in 2012, what they found is this membrane, if you seal it well, it's very permeable to water vapor, compared to hexane, ethanol, but also like helium gas. So water can cross very efficiently this membrane while it can block helium. So this was at that time very, very interesting. And they later showed that this membrane can be used to sieve molecules in water, and the main mechanism is based on size limited diffusion of the species. So here you have the diameter of the species, and here this is the flux, the permeation rates. You see the high permeation rates from the smallest molecule or ions, so like potassium. Then when you increase magnesium, propanol, sucrose, which is a lot bigger, then you have a huge drop of the permeation rates. And the cutoff is about, I think here is slightly higher than 4 angstrom. So anything larger than 4 angstrom could be blocked, okay? Which is good because in principle you can block hydrated sodium, so you can use this membrane for desalination. The main problem with this membrane is graphene oxide is very hydrophilic, and the water will just penetrate in the capillaries, swell, and then you lose the spacing between the nanosheets. And at the end you lose the control of the sieving. So the approach, actually the same group more recently, 2 years ago, they proposed to control the swelling by encapsulating this membrane in epoxy. So they use an epoxy matrix to encapsulate the nanosheets. So the nanosheets are in black here, so that the membrane cannot swell even if you dip it in water. And this way they were able to control the space and control at the end the sieving performance of those membranes. And so this is another example in the literature, just summarizing what I've just mentioned. So the problem with graphene oxide membrane, as you see here, this is T equals 0 minutes. After 30 minutes, the swelling is so intense, so large, that it dramatically affect the membrane, the nanosheets, the laminates, and redisperse in solution. And this is after 1 day, so the membrane, the integrity of the membrane is gone. And then here you see the despacing of this membrane. So this is the space between two layers of graphene oxide. So in the beginning, when it's dry, it's about 0.9 or 0.8 nanometers compared to 0.3 for graphite or 2 graphene layers. As you soak in water, then progressively increase to 6 nanometers. So 6 nanometer, you can still sieve a lot of things, but you cannot use this membrane for removing salts, desalination, for example. At the opposite, there are some reports about molybdenum disulfide, and the situation is reversed, where when the membrane is dry, since you don't have these functional groups that you have in graphene oxide, the membrane cannot swell, and the stacking is so close to bulk that there's no way any molecule, even gas, can go through these nanocapillaries and can diffuse. So when it's dried, it's basically a barrier and not a membrane. So you want to be in between, where you have some spacing, where this spacing allows some molecule to diffuse and block the others. So the approach was to use this functionalization. So the functionalization, we can use this to increase the space between the nanosheets, because now we have these functional groups that can be used like a kind of as a brush, so that it increase the space between the nanosheets. And we can also functionalize with different functional groups. Now we're trying with more functions, but methyl is very hydrophobic, and this is the most hydrophilic molecule that we have tested. And of course, we can change the size of the length of this alkyl chain, but in this first study we didn't investigate this parameter. So we confirm we have common functionalization with NMR. So this is the peak. I will just ask you to focus on this peak here. This is from this carbon. This is this carbon NMR, and this peak here again is coming from this carbon that is initially bonded to the iodine group. After functionalization, it's bonded on the sulfur atoms, so the environment changes, and you see that this peak now is shifted to like 50 ppm. So this clear shift is showing you have common functionalization. And we made a membrane by vacuum filtration, so nothing new here. We follow the same protocol as Nayer's group in Manchester. And we use a polymer substrate which is flexible, because the mechanical properties is still not enough to stand like 5 to 10 to 15 bars. So we use a polymer substrate, so this makes also membrane flexible. We see here the cross-section images, so we have high degree of alignment of the nanosheets. We check the spacing, the despacing, so the spacing between the nanosheets by X-ray diffraction. So this is the non-functionalized membrane. So this corresponds to around 14 degrees, which gives you a spacing of 6.3 angstrom. Assuming a thickness of 15 angstrom for bulk MOS2. The difference between bulk MOS2 and exploited restacked MOS2 is only 0.15 angstrom. So this is not enough for water to diffuse. Water molecule is about 1.8 angstrom. And after functionalization, we shift this peak because now we have these functional groups which increase the size, which increase the despacing between the nanosheets. And as a consequence, this peak here is gone because we have completely functionalized the nanosheets, and it's moved towards lower angles, so higher spacing. This peak here is the second order of this peak. And now we can control the spacing of the nanosheets from 10.6 to 11 angstrom. So if you subtract thickness of one single layer of MOS2, the capillary width, so the space between two nanosheets that is accessible for water molecules is between 4.5 angstrom to 5.3 angstrom. So this is enough for water to diffuse in. And since we can control the surface chemistry, which is not possible with graphene oxide, by the way, we can tune the contact angle. And of course, we found the highest contact angle for this hydrophobic group, such as methyl. And we can tune, so MOS2 in the beginning is quite hydrophilic actually. And then the second one is acetamide, which is hydrophilic, more hydrophilic compared to ethanol and of course methyl. So this contact angle shows that we can control the surface chemistry. And most importantly, we can control also the swelling. So you see the swelling percentage of graphene oxide after 16 hours in water is about 65%, compared to 0 for MOS2 or close to 0. And in the worst case, I think it's around 15% for ethanol functionalized MOS2. And then we measure the permeation of water as function of the thickness of the MOS2 membranes, and you see different behavior, which is quite interesting and unexpected, I would say. So water molecule cannot cross MOS2 membranes. After functionalization, we have, in all the cases, we have flux of water, and the flux decreases as the thickness increases. This is what you expect for membrane. But in the case of methyl groups, we see kind of the opposite trend, where it seems the water permeation increases, or at least gets stable. We still not sure whether it increases or get stable, but the trend is clearly different. And we recently changed for propyl functions, and we observe the same trend. So we believe this is more related to hydrophobicity of the membranes. And to further understand, we collaborated with Nicolas Onofrio. He's a professor at PolyU in Hong Kong, and he used molecular dynamics to predict the influence of the surface chemistry and influence of the spacing on the water permeation. So we make this cell where you have here two MOS2 nanosheets. So use this shape because it's easier for the calculations. And you put the water molecule, and you can apply some pressure on both sides. You can apply different pressures, so we can create, and for the calculation, a gradient of pressure. And you can count the molecule that cross the middle of the cell here. This is here for just pristine MOS2 with different spacing from 10 angstrom to 20 angstrom. You see in the beginning when it's 10 angstrom. So experimentally we found, if you remember, we measured 6.3 angstrom. So here we are already higher than the non-functionalized case, but still there's no water crossing for this spacing because there's not enough space for the water to permeate, so it makes sense. But as you increase the spacing here, the flux increases rapidly, and we found that it's scaled as a power of 3, which is very similar to the Poisson equation for fluid dynamics. And then he investigated the influence of the surface chemistry. So here this is the same despacing, just different functional groups. So this was for, I think, 20 angstrom channel height. And you see that the highest flux is actually obtained from methyl compared to ethanol, acetamide, and pristine MOS2. So pristine MOS2, there's a flux because it's 20 angstrom, so that's why. If it's 10 angstrom non-functionalized, it will not pass. But very interestingly, we found that methyl groups shows the highest flux, and we believe that it's because this hydrophobicity decreases the friction between the water molecule and the methyl groups. So the methyl, the water can kind of slide on the surface of functionalized MOS2 with less friction than the other molecule. And this is also what has been reported for graphene, which is expected to give very long slip lengths. So the water can slip on graphene because graphene is highly hydrophobic. So we got very similar results, but here this is the nice thing here is we can control the surface chemistry to really investigate this parameter. What is very interesting, and I will finish with this, is we can investigate the rejection. So with water we add some contaminant, so it can be like small molecule like caffeine, acetaminophen, which is a paracetamol drug, up to like organic dye. So we increase the size. We got close to 100% rejection. So for the smallest molecule like acetaminophen and caffeine, the rejection is slightly less than 100%, around 95%, but I think this is still promising. And we also look at the salt rejection. So we measure the salt that cross the membrane, and this is the water flux. And we found that the flux is typically from 10 to 60. The highest is 40 ml, 40 liters per hour per meter square per bar. And so you see that the rejection performance is actually significantly improved compared to other types of membranes, such as 2D graphene oxide or CNT, or just graphene oxide or just CNT. And we are approaching commercial membranes. Of course, this is different scale, so there's a lot of work to be done to bring this to the market. And I think I will go quickly on this, but we can also control the defects. So what we did is we synthesized these nanoflowers of MOS2, and then we treated these nanoflowers under hydrogen at high temperature. As you increase the annealing temperature on a hydrogen atmosphere, you will create more sulfur vacancies. And by controlling the temperature, we can control the amount of vacancies that we create. So here we use very simple TMDs that have been grown by hydrothermal reactions. So just the parameter we want to investigate is the influence of the nature of the defects. And we can follow the defects by performing XPS. And this is the sulfur peak from S to S. And you see, as you increase the temperature, you see this peak decreases. And especially, sorry, this is 400 degrees, 500, 600, 700, and so on. What we observe is up to 600, we have a slow decrease of the sulfur content in the MOS2 nanosheets. But after from 600 to 700, then we completely decrease, or we almost remove all the sulfur atoms from the MOS2 nanosheets. This is what you see here on the summary. This is the S to MO ratio. So in the beginning it's 2 because MO is 2. As you increase the temperature up to 800 degrees, then you see in the beginning you have a small or slow pace increase of the sulfur vacancies, and then after you decrease dramatically the amount of sulfur, so you create a lot of vacancies in the material. So we believe here we have more like point defects, whereas here we are like stripping the sulfur away from the nanosheets. And then we measure the electrocatalytic activity. We'll skip this, but this is the turnover frequency, so this is basically the activity. And we measure this at different temperature and also at different sulfur to molybdenum ratio. And what we found is we can identify the two regions that we have observed by XPS. In the first region, where we have these point defects, we have a very fast improvement of the TOF, so in black, and a very fast decrease of the overall potential. So the potential you need to apply, you need to supply to your electrodes decreases, and the activity, the TOF, increases. The other regions, when you strip away the sulfur, we can still improve the activity, but at a slower pace. So this shows, this is at pH 0, this is at in alkaline conditions. We have both, in both conditions, we have the same effect. So this shows, or this suggests that we have a difference of behavior if you have point defects or large defects. So we believe that this, again, preliminary results can help people to design novel catalysts based on 2D materials by controlling the quantity and also the nature of the defects. Okay, so with this I will just wrap up all I've shown you today. So we can, I hope I've convinced you that we can engineer the structure of exfoliated three-dimensional materials, and especially these TMDs. We can use these engineered TMDs, exfoliated TMDs, for many applications, and the nature of this engineering will be useful for some application or some others. So we can, we have shown we can use phase engineering for electrocatalysis and electronics. We can use functionalization for example, to investigate some nanofluidic behavior within the 2D capillaries. We can maybe use this also to this functionalization of defects to engineer the optical response from the single layer TMDs. And what we are trying to do in my group is to combine some of these properties to develop novel membranes that can be optically active or electrocatalytically active. And with this, I will thank some people in my group. So this is my PhD student that works on this MOS2, functionalized MOS2 membranes. And Dr. Riley that works on this defect MOS2 for HER. And my postdoc fellow that was here last year to work on electrical catalysis, some master student, and my previous advisor in the US, Professor Manish Chawla, who's now at Cambridge, and some collaborators from PolyU Hong Kong and Picatinny Arsenal in the US. And thank you for your attention.
Time for a few questions.
Very short question. At the beginning of your talk, you were talking about the phase transition of the materials, about, for example, molecular disulfide. You are saying inserting the lithium and you can change the phase. How you can insert the lithium into this material? Via physical or chemical process?
So you can do either way, chemically or electrochemically. So you will intercalate if you have multi-layer sample. So if you have bulk or bilayer, if you reduce your material, if you reduce your nanosheets, so this means you will transfer one electron. So again, it can be chemically or electrochemically, but you will transfer one electron to your nanosheets. So your nanosheets will have one electron excess. Now you know that you cannot have just material that is negatively charged sitting around. Okay, so you need to compensate this negative charge with a positive charge. And that's why the lithium penetrates between the nanosheets or at solvent surface. Okay? Right, to ensure the material overall remains neutral.
For membranes, for the filtration purposes, can they recycle?
We didn't investigate, so you mean recycling as, so we didn't investigate any fooling effect, if this is what you're seeking. So we don't know. But we won't use this membrane. If there's any application for this membrane, we won't use directly from the pipe, right? So there will be other membranes before, and then this membrane can be used just at the end to remove this the salt or to remove some nanopollutant, micropollutant. So in that sense, it will be, you can use it for a longer time. If you use very dirty water, this will be dead within 1 minute for sure. But if you use this nanopollutant, the concentration in water typically is 10 to -6 mole or something. So I believe we can use longer, but I don't have number for that. But probably we have the same issue as the others.
As you shown earlier, that if we keep on annealing MOS2 at 300 degrees centigrade, there will be a significant phase shift. So in the previous last slides, you shown that when we expose MOS2 to the hydrothermal reactions, it will at 400 degrees centigrade. So will there be again any significant phase shifting under hydrogen environment?
No, we didn't have any evidence of this. So I was very fast on this, probably too fast, but we synthesize by hydrothermal reactions, but the material is actually more amorphous from the X-ray diffraction that we observe, that we have. So what we did is to make sure it's highly crystalline and 2H, we anneal the sample at 800 degrees under argon, pure argon. So in this case, we don't make defects, but we kind of recrystallize the material. And then at 400, we do under hydrogen, from 400 to 800, after this 800 degrees argon. So we know that there's no 1T phase because we have annealed at very high temperature in the beginning. So we have 2H phase, 100% 2H phase. And we confirm this by Raman and XPS and so on.
So at the beginning of your presentation, you showed that tungsten disulfide goes through phase transition from H to T phase. So what I'm wondering about is, does the phase transition can intercalation, or does it happen after chemical exfoliation?
No, after the intercalation.
After the
So we can stop the reactions after the intercalation and recover the intercalated powder. Or we can now, we've developed some methods to grow directly intercalated crystal. And we have the peak, the Raman peak from this 20 phase. Actually, the Raman peaks that we detect are from this distorted 20 phase. There are some theoretical papers about this phonon dispersion of the 1T phase or 1T prime phase, and they've shown that the Raman signature that we see is from this distorted 1T phase.
Right, let's thank our speaker one more time.